We want to now make a quick aside to describe quality factors in damped oscillations. So remember that we had this term for finding the energy in simple harmonic motion, where the energy itself was a factor scaled with the square of the amplitude. When we have damped simple harmonic motion, we're now working with a decaying exponential. Remember, this exponential term here now describes the amplitude. So we can find an expression for how the energy decays in damped simple harmonic motion. When we start our oscillation, E0 is our initial undamped oscillation, and we can find out at any time how much energy remains in the system using this decaying exponential. And this is where the characteristic decay constant 2 tau becomes apparent. It makes it easier to work with the mathematics. So what we see is that the amount of energy in the system decays exponentially with time. So that should be no surprise to us. Remember, the envelope decays exponentially, the amplitude decays exponentially, and the square of an exponential is still an exponential, so we would see that exponential decay. The quality factor is a way of describing the oscillation. It's a way of summarizing a number of complex factors into a single term. The quality factor, simply put, indicates the persistence of the oscillation. It's the angular frequency multiplied by that characteristic decay term, tau. If we have a large quality factor, so high quality oscillation, we have light damping and quite a persistent oscillation. A small q is a low quality factor, heavier damping, and the oscillation decays rapidly. The easiest way to explore this is by exercise. So let's have a look at our SHM. So what is the minimum value of Q that still allows for an oscillation to take place? Pause the video and we'll come back to it once you've got a solution. Okay, so we go back to our damping term, and if we remember that we had our critical damping constant B is equal to 2m omega 0. That's the point where we have zero oscillation taking place. Anything smaller than that, we will still have an oscillation. Anything bigger, we have overdamping and no oscillation takes place. So that critical value is what we need. So let's pop that value of B into this equation here, and we get an answer of Q is equal to 0.5. So for anything where we want to still have an oscillation, the minimum value of Q has to be greater than 0.5. Anything of 0.5 or lower will stop the oscillation dead. This quality factor relates to the energy loss per cycle of oscillation. So we said earlier on we had the decay of the energy with respect to time. We can find the rate of energy loss by finding the derivative of this with respect to time, and we find that the rate of energy loss is equal to the energy divided by that characteristic decay constant. We can approximate this term by looking at a measurable energy change. So the change in energy divided by the period is approximately equal to the rate of change of energy, which is approximately equal to the energy divided by the characteristic decay constant. Why are we doing this? Well, let's bring it forward into the next step of the derivation. When we take this term, this expression for the rate of change of energy, we can say that we have an expression for t, which is 2 pi over omega 0, divided by the characteristic decay constant, and we can relate the change in energy to the quality factor. What this means is that the quality factor is inversely proportional to the fractional energy loss. This term, delta E by E, is the fractional energy loss per cycle. It's the amount of energy that's lost as a proportion for every cycle. So what that means is that the higher Q, the less energy loss we have per cycle. The lower Q, the greater the energy loss we have per cycle. This is a simple way of considering the quality factor, and it gives us a single value which allows us to summarize a whole load of complex aspects of an oscillation. We'll use the quality factor at numerous points through this course, but this aside should hopefully help you understand what we mean when we talk about the Q factor.